A city has always been an information system. Long before computers existed, streets carried information about movement. Markets revealed demand. Ports measured the flow of goods. Railway timetables synchronized entire regions. Buildings recorded the changing needs of the people who occupied them. But cities have always had one fundamental limitation. They could not see themselves as a whole. By 2035, that may begin to change. Sensors embedded in buildings, roads, vehicles, and infrastructure are creating an increasingly detailed picture of urban life. Artificial intelligence can analyze that information, while digital twins can represent the physical city as a continuously updated computational model. The result is something different from the conventional idea of a smart city. Instead of simply collecting information, the city begins to interpret it. Instead of waiting for problems to appear, it can begin to anticipate them. And instead of treating buildings, transport, energy, and water as separate systems, urban intelligence can begin connecting them. The city becomes observable, then predictive, and eventually, increasingly responsive. The first generation of smart cities was largely about visibility. Sensors collected data, dashboards displayed it, algorithms identified patterns, human operators made the decisions. That model remains important, but a new architecture is emerging. The distinction is where intelligence sits within the system. An AI-native urban system can increasingly observe conditions, analyze them, make recommendations, and within defined rules, trigger a response. McKinsey describes this shift as a move from infrastructure that primarily observes and reports towards infrastructure capable of continuously operating and responding to conditions in real time. That changes the role of architecture. A building is no longer simply an object designed to perform a fixed function. It can become a responsive system. Its facade can respond to solar conditions. Its ventilation can respond to occupancy and air quality. Its lighting can respond to daylight and activity. Its energy systems can respond to demand. And its digital model can be used to test how those systems behave before changes are made in the physical building. Architecture begins to acquire something it has never possessed at this scale: a feedback loop. At the center of this transformation is the digital twin. The concept is deceptively simple. Create a digital representation of the physical environment, connect it to real-world data, and use the model to understand how the system behaves. But at urban scale, the implications are enormous. A digital twin can combine information from sensors, geographic information systems, building models, transport networks, utilities, and environmental monitoring. It can represent not only what exists, but how the city is behaving, and increasingly, it can simulate what might happen next. Research into urban digital twins is already exploring their use in planning, infrastructure optimization, resource management, resilience, and scenario simulation. Imagine a city preparing for an extreme heat event. Instead of simply issuing a warning, the urban model could simulate energy demand, identify buildings likely to overheat, estimate pressure on the electricity network, predict vulnerable transport routes, and determine where cooling resources would have the greatest effect. The city does not wait for the event to happen. It rehearses it first. That is the deeper significance of the digital twin. It turns the city from something that is merely observed into something that can be simulated. The transformation will not happen only at the scale of the city. It will begin inside individual buildings. For more than a century, architecture has largely been designed around fixed systems. Walls stay in place, windows open or remain closed. Mechanical systems operate according to schedules. Lighting follows programmed settings. By 2035, many buildings could operate more dynamically. Sensors can determine where people are. Environmental systems can monitor temperature, humidity, and air quality. AI can learn patterns of occupancy and energy demand. Building management systems can coordinate heating, cooling, lighting, ventilation, and storage. The facade itself can become part of the control system. A building facing the morning sun does not need to behave like the same building at midnight. Its response can change continuously. The architecture remains physical, but its behavior becomes computational. This is an important shift. The intelligence of a building is no longer necessarily visible in its appearance. It exists in the relationship between structure, materials, sensors, software, and energy. The most advanced building of 2035 may not look dramatically different from one built today. It may simply respond differently. The real transformation begins when these intelligent buildings connect to one another. A building consumes electricity. A transport system consumes electricity. A data center produces heat. A battery stores energy. A solar installation produces power. A water network requires pumping. A district has changing patterns of demand throughout the day. Today, many of these systems are planned and operated independently. Urban intelligence creates the possibility of coordination. A city could shift energy demand away from periods of peak consumption. Electric vehicles could become mobile storage resources. Buildings could reduce cooling loads when the electrical network is under pressure. Street lighting could respond to movement rather than operating at a constant intensity. Waste collection could respond to actual demand instead of fixed schedules. Transport systems could adapt to changing passenger flows. The principle is simple. Do not make every system work harder. Make the systems work together. This is where the architecture of the city begins to change. The most important infrastructure may no longer be visible above ground. It may be the digital layer connecting everything beneath it. Consider the street. For much of the modern era, streets were designed around relatively predictable patterns. Roads had fixed lanes. Traffic signals followed programmed cycles. Public transport operated according to timetables. Parking occupied valuable urban space, whether cars were present or not. Urban intelligence introduces another possibility. The street can respond to demand. Sensors and connected systems can identify congestion as it develops. Traffic signals can adapt. Public transport can respond to passenger volumes. Road space can potentially be allocated differently at different times. And as autonomous and connected vehicles develop, the relationship between vehicles and infrastructure could become increasingly coordinated. The result may not simply be faster transport. It could change the physical design of streets themselves. If fewer areas require permanent parking, land can be returned to pedestrians, cycling, public space, or development. If transport becomes more responsive, cities may require less road capacity for peak conditions. If streets become multifunctional, the boundary between infrastructure and public space begins to disappear. The intelligent city is therefore not necessarily a city with more technology. It could be a city that needs less physical infrastructure because the infrastructure it has is used more efficiently. Perhaps the greatest architectural consequence will occur before construction begins. Traditionally, urban design depends on drawings, models, simulations, and professional judgment. Those tools are becoming increasingly interconnected. An architect can model sunlight. An engineer can model structural performance. A transport planner can model movement. An environmental consultant can model heat. A city authority can model infrastructure demand. Urban intelligence can bring these systems together. Instead of evaluating one design at a time, algorithms can explore thousands of possibilities. Where should a building be placed? How tall should it be? Where should trees be planted? How should streets be oriented? Where will heat accumulate? Where will wind become uncomfortable? How much energy will the district require? How will a new development affect transport? The computer does not replace the architect. It changes the design space in which the architect operates. Architecture becomes less about selecting a single solution from a limited number of possibilities, and more about defining the parameters within which an intelligent system can search. The architect increasingly becomes the designer of relationships. The greatest value of urban intelligence may not be convenience. It may be resilience. Cities are facing increasingly complex combinations of environmental and infrastructural pressures. Heat, flooding, water scarcity, energy demand, aging infrastructure, population growth. Urban digital twins and AI systems are being investigated specifically for planning, resilience, sustainability, and scenario testing. A conventional city responds to disruption after it occurs. An intelligent city can begin preparing before the disruption arrives. A flood model can identify vulnerable streets. A heat model can identify neighborhoods where temperatures are likely to become dangerous. Infrastructure sensors can detect deterioration before failure. Buildings can reduce energy demand before the grid reaches critical levels. Emergency services can receive a continuously updated picture of the city. The objective is not to eliminate uncertainty. Cities will always contain uncertainty. The objective is to make uncertainty visible early enough to act. But a city that can see more can also watch more. And a city that can predict behavior raises a fundamental question. Who controls the intelligence? Urban systems depend upon data. The more connected the city becomes, the more valuable that data becomes. Where people travel, how buildings are occupied, how energy is consumed, how public spaces are used, which areas are experiencing problems, which systems are failing. Without clear governance, the intelligent city can become a surveillance city. There are also questions of cybersecurity, interoperability, algorithmic bias, privacy, and unequal access. And there is another danger. Technology can optimize what is easy to measure, but not everything that matters in a city can be reduced to a data point. Belonging, beauty, memory, social interaction, the character of a street, the experience of walking through a neighborhood. A city is more than its operating system. Intelligence must therefore serve urban life rather than become its purpose. By 2035, the intelligent city may not look like the futuristic cities imagined in the 20th century. There may be no universal visual language, no single architectural style, no obvious dividing line between the old city and the new one. Instead, intelligence will be distributed inside buildings, under streets, across transport networks, within energy systems, through water infrastructure, inside planning departments, and increasingly within the software that coordinates them. The transformation is therefore not really about making cities smarter. It is about making them more adaptive. A building that responds to its environment, a street that responds to movement, an energy network that responds to demand, a transport system that responds to people, a planning model that can test the future before construction begins, a city that can detect problems before they become failures. That is a different conception of architecture. For centuries, architecture has been concerned with permanence. We designed buildings to withstand change. The next generation may be designed to respond to it. The distinction is subtle, but profound. A static building performs. An adaptive building responds. A static city operates. An intelligent city learns. And the most advanced urban environment may eventually become one that does not simply contain human activity, but continuously adjusts itself around it. The challenge will be deciding where that intelligence should stop. Because a city is not a machine to be perfectly optimized, it is a human environment. Messy, unpredictable, layered with history, full of contradiction. Its value does not come from eliminating uncertainty. It comes from giving people the freedom to live within it. By 2035, urban intelligence may therefore reshape architecture in a way that is almost invisible from the street. The facade may still be glass, the road may still be asphalt, the building may still look like a building. But beneath the physical city, another city will exist. A continuously updated model, a network of sensors, a layer of algorithms, a system capable of observing, predicting, and responding. For thousands of years, humans have built cities to control their environment. The next stage may be different. We may begin building cities that can adapt to it.
1,000 moments lost their frame, as if our past was just renamed. Dates are wrong and the colors fade, promises marked as never made. Your laughter echoes but something's gone, like the sound was trimmed too long. If I could find the first edition before the edits took their toll, before the silent revisions changed the language of our souls. But every backup fails tonight, every copy fades from sight. You left a corrupt fire where love should be, a fraction map of